Hey everybody, my name is Emmanuel. I work at Google in the Munich office, and today I'm going to be telling you about NativeIO, our new storage API that has a particular focus on performance and genericity. So first things first, what is that we're trying to solve? What are we doing here? The challenge that we're trying to tackle is to give developers a storage primitive that brings some of the good things you see in native platforms while preserving all of the good stuff from the web that we know and love. That is to say, we want to give developers storage that is both very flexible, very performant, but also secure, private, interoperable, and all the good qualities we're used to. Some of the use cases where we see NativeIO helping out are, for example, enabling you to bring true and tried technologies such as SQLite, LevelDB, or your own favorite database to the web. And this works because NativeIO, due to its characteristics, is able to work as a backend for these kind of libraries. We also see NativeIO as enabling a fast and persistent file system for WebAssembly. This is in the realm of ported code, legacy code that has certain expectations about how both data is accessed and the speed with which this data is accessed. And NativeIO is able to comply with those expectations. But we not only see NativeIO in this realm of ported code, WebAssembly, we also see it as a way to empower developers to have fine-grained control over the way their application controls the data it's processing. So if a developer wants to squeeze as much performance as possible and wants to implement exactly the right storage algorithm they need to fit their needs, NativeIO's flexibility and low-level building blocks are there to help. So without further ado, this is how our interface looks like. NativeIO is divided in two parts. Here on the left-hand side, you can see the file system operations, and this is a very thin management layer that controls the creation, deletion, renaming of files. And with it, you can also list all the file names that belong to an orator. On the right-hand side are the file operations, and that's where the magic happens. So if you'll see, the first two functions are read and write. These are the most important ones. They take a shared array buffer to minimize copies of the user data. And they take an offset to be able to move these buffer around the existing file. With file operations, you can also modify the length of a file. With flush, you can ask NativeIO to move the contents of a file into the disk, and you have fine-grained control over that. And of course, we have a close to avoid resource leakage. In the next slide, I'm going to show you some examples of these operations being used and highlight some of the constraints that we're thinking of applying. So following the same format, here on the left-hand side is an example of file system operations, in this case, get all and rename. And what it does is simple. I'll walk you through the flow. First, we create two files, hello world, and you can see them by listing them. And then we're going to rename them. First, we close hello, we rename hello to small, and when you list them, you get the expected result, that is small world. Here on the right-hand side is an example of file operations, write and read. And I'll also quickly walk you through the flow of that code. So first we ask NativeIO to open file foo. Then we also create a buffer, in this case, one containing 3 bytes, 010. And then we ask if open file handle to write this buffer at position 0. Now, to make sure we don't lose our precious data, we also ask the handle to flush this information. And then now we're sure it's going to be persisted. Now, to do the reverse, we also create a read buffer. And we ask the file handle to please read 2 bytes, that's the length of the buffer, starting at offset 1. So as you say, it's a relatively simple API. It does what you expect. And now I'm going to highlight some of the constraints that I put in here. So if you see on the left-hand side, hello has to be closed before being renamed. In general, most file system operations require the file handle to be closed, or rather, there are no open file handles to the file. And this also implies that when opening a file, there cannot be other open file handles. That is to say, you can only open a file one at a time. We put this in place to simplify the spec and also to try to prevent race conditions and these sort of nasty bugs. But it's one of those things where we're trying to find a balance between performance and the interface. So this might be something that we'll reconsider. Another thing to note is that opening a file, if it doesn't exist, also creates it. As well as on the right-hand side, you'll see that the length of the array actually determines how many bytes you're going to read. So those are some of the details that I wanted to highlight in how it is used. That is all I have for you on the technical side. I'll give you a small summary of where we are right now and where we're looking forward to go in the future. So NativeIO has received enthusiastic partner feedback both inside and outside Google, which made us pretty happy. It means that we're probably fulfilling a need that's there in the platform. We have a full prototype behind a flag in Chrome, so you can go and try it right now if you want. And we also have an mscript and file system that makes it easier to try NativeIO if you ever want to use it from C or a C++ application that you're porting to WASM. Now, on the open questions side of things, these are places where we're going to put some effort in the future and where it will be great to get some feedback, although feedback in general is more than welcome. So the first one is around benchmarking. We put some effort in benchmarking at the beginning to validate our design. We compared general performance of NativeIO against some of the legacy storage APIs. And indeed, it seemed NativeIO is fast and we're in the right direction. We also put more effort into exploring the difference between a synchronous and asynchronous interface. And this has to do with the performance from within a WASM application. But the open question right now is, what would be a good benchmark that really testifies to NativeIO performance in general and in the context of the modern web platform? We've considered TPCC on top of a ported database. We've also been using a SQLite specific test called speed test, but pointers or ideas of what is a good, reproducible, trustworthy way of benchmarking would be great. The next open question that we wanted to pose was, what are other use cases that might benefit from NativeIO that are out there? So I mentioned porting these trusted libraries such as SQLite to the web. I mentioned providing a fast and reliable file system for WebAssembly, and also this fine-tuned control for developers regarding storage. But there might be other things out there that we don't know about that might benefit from NativeIO, and hearing about them would be great because we could also consider them during our design process. Now, last but not least, this being TPAC, we would love to hear what we could do better in our API surface. So improvements to our interfaces, recommendations or comments would be great as well. That's all I got for you today. So in general, feedback is very welcome, either here in this meeting, or you can also reach out to us in our Discourse or in GitHub issues in our explainer. And that's all I have for you today. Thanks.